Welcome to the Physics 104 Data Analysis and Graphing Lab. And the purpose of this lab is a bit of a refresher for you folks to practice your basic data acquisition and graphical analysis skills to try to mathematically quantify a simple physical relationship. That relationship has to do with the period of a simple pendulum, which consists of a length of string connected to a point mass. And in front of you, I have two different pendula. One is made out of aluminum, the other is made out of brass. And if you were to ask people to guess what the period of a pendulum might depend on, many people will guess that it would depend on the mass, with the heavier pendulum having a faster period. Let's see if that's the case. What I'm going to do is I'm going to displace these from equilibrium by about the same angle and release them. And what you see is that these remain in sync. So the period of a pendulum clearly is not mass dependent. What then does it depend on? Well, as it turns out, it's very strongly dependent on the length of the pendulum. So what I'm going to do is I am going to shorten the aluminum pendulum here. We're going to repeat that same demonstration here. So I'm going to displace them from equilibrium by about the same amount, release them, and you can see that they immediately start to drift here, and that the periods are very different. Notice that the pendulum that has the shorter length oscillates back and forth more rapidly. It has a shorter period than the pendulum with the longer length. So that's what we're going to try to quantify. We're going to try to come up with a mathematical equation that describes that. Now, had we been doing this as an in-person lab, how you would have acquired the data would be as follows. What you would do is you would measure the length of the pendulum from the support point here down to the midpoint of the pendulum bulb. You'd record that length, and then using a stopwatch or a timer on your phone, you would measure the period. Now, to be very clear about how the period is measured, here's how it works. Right here, we are in the equilibrium position. You're going to displace it the maximum amount from equilibrium. That's at the peak of the amplitude of the swing. You'll release it so that it goes through equilibrium, swings through to the other side, swings back through to equilibrium, and back to that initial release point. That complete cycle is one period. So again, from here forward, back to here, one of these to and fro oscillations is one period. Since you're doing this as a remote online lab, we're going to try to replicate this using an applet. So next, let's take a look at how that works.
Okay, so I am here at the Physics Educational Technology, or PhET website, and we're going to launch the Pendulum Lab applet here. The applet has a number of different modes, and for the purpose of our lab, you're going to go for the intro mode. And what we have here is basically a simulation of this little pendulum, which you can drag and release, and it will oscillate back and forth just like the pendula we looked at in the lab. On the left-hand side of the screen, we have a number of measurement tools. So you have a little ruler here, which you can use to measure from the support to the center of the pendulum bob. And you get a little stopwatch that you can activate to record or measure the period of the pendulum. So I can pull this back and release it. And just like that, I can record its period. Now, that probably happened fairly quickly, so let me show you this again. I'm going to reset it. I'm going to wait till the pendulum goes to the point of maximum amplitude, start recording the period, and then I'll measure one period of that. So there we go. So that still happens pretty quickly, and human reaction time is going to be a major source of error if you rely on just that one reading. One way to address that is that rather than measuring the period for one swing, you could measure the period for, say, 10 swings, and then divide that by 10, and that'll help. But there's another thing that you can do here. Down here at the bottom is a slow motion option, which will allow you to measure the period of the pendulum as it oscillates in slow motion. So if I start it here, note that both the pendulum simulation as well as the stopwatch operate in this slow motion mode. So you can use that to basically increase the accuracy of your period measurements. On the right-hand side here, we have some different measurement options for you. So you have a slider here that can change the length of the pendulum between 0.1 and 1 meter, and just by adjusting that slider you can adjust the length of the pendulum. If you want to try to recreate that experiment that I demonstrated showing how the mass affects the period or not, you can play with the mass slider. Here we have the measurement for the Earth's gravitational acceleration, something that I'll talk about in the analysis portion of the lab here. Right now, this is set so that it's measuring the Earth's normal gravitational acceleration. You could set it as if you were doing the experiment on the moon or on Jupiter, or some arbitrary value, whatever you would like. We're going to deal with what we call an idealized pendulum, one that is not subject to any friction or air resistance, but if you're curious to experiment with those options, you can try to increase that and see what it does. So you're going to use this applet, and you're going to follow along with your lab manual, and basically what you're going to do is you're going to choose a number of different lengths between 0.1 and 1 meter. You're going to measure the period for that length, enter it into your data table, and then you'll move on to another new length, another new period reading, and so forth. And then we're going to try to mathematically describe that relationship. So let's take a look at how the analysis works next. Okay, so we've seen the applet. What I want to take a look at now is the data analysis that we're going to be doing in the lab. And so we've seen that the period of a pendulum depends on its length. But what we want to know is exactly how it depends on the length. So I'm going to give you a little bit of theory here. As it turns out, the period of a pendulum, which we give the symbol t, depends on its length through the following mathematical equation. T is 2 pi times the square root of length over g. I'm not going to explain at this moment where that comes from. That's something we'll deal with a little bit later on in the course. We're going to focus right now on just essentially testing whether that equation is valid. Now, the g in this equation, by the way, is the gravitational acceleration, 9.8 meters per second squared, which you might recall from previous courses. It's a constant. And so in this experiment, we basically have two variables that we can tweak, the length and the period. And we can rewrite the equation so that the constant pieces are all together. Now, if you think about what we've been doing in this experiment, we have control over the length. That is what is called the independent variable. And if you try to graph something, which is one of the things we're going to be doing next, your independent variable is going to go on your x-axis. The period is what depends on the length. It's called the dependent variable, and it goes on the y-axis. So essentially what we're doing in this lab is to try to verify this equation. We want to see graphically whether this equation has essentially the right shape. And we'll see that there are certain types of shapes of graphs which would indicate that period depends on the square root of length. And we're also going to use this to try to find a value for the acceleration due to gravity. So, what you're going to do is you're going to work with the applet, and you're going to gather data for different lengths of pendulum, and you're going to find the period. And what you're then going to do is you're either going to graph by hand or using a graphing program like Microsoft Excel, and you're going to produce a graph of the period versus the length. And the graph you get should look something like this. You may be used to sort of straight line graphs from previous physics courses. Here, you're going to have a curve, and in fact, we're going to see that the curve is exactly what you expect. So you're looking for that kind of curved shape. Now, what do you do with the curved shape? Well, we're going to have to do something called linearizing this graph, and how we do it is as follows. In your lab manual, you have a figure here, which is basically indicating how to linearize a graph. And what you first do is you plot your dependent variable against your independent variable, and you look at the kinds of shapes you get. So you're going to see something like this curved shape like this. What your lab manual tells you to do then is to plot a graph of y, or in our case, period, versus length to the 1/2. That's the same as the square root of length. So how do you do that? Well, what you'll have is you'll have this data table. You will first calculate the square root of the length for all of these values here, and then plot the period against the square root of the length. And what you should get is something that looks nice and like a straight line, a linear graph like what I'm showing above here. If you get that, this is a demonstration that the period depends on the square root of the length. That's one of the things we're trying to do with this lab. The second thing we're trying to do is we're trying to find a value for this gravitational acceleration. And so to do that, we're going to have to look at the characteristics of linear graphs in a little bit more detail. So let's take a look at this graph. What you hopefully remember from math and physics courses is that when you have a graph like this, the graph of a line, it has this very characteristic equation, y equals mx plus b. Your y here is your y-axis variable, your x is your x-axis variable, m is the slope of the graph, and b is, it's called the y-intercept. That's where, or the value on the y-axis where that graph strikes the y-axis. In our graph here, you can see that that is pretty close to 0. How does this help us? Well, let's go back to thinking about what we're actually measuring. What we are actually measuring is a graph of period against the square root of length. So I'm replacing y with period, x with square root of length. What I see here then is that my slope of the graph is the value here, this m value, and if you get a graph like mine, your y-intercept will be very close to 0. So we're basically modifying this equation to what we're actually plotting. Let's now compare that against the theoretical equation. So we're matching up all of these pieces. And if I go to the theoretical equation, I'm starting to get something that resembles that theoretical equation. Because according to theory, the period should depend on the square root of length, and there shouldn't be this kind of y-intercept piece. It shouldn't be there. Not only that, but that slope of the graph here should be 2 pi over root g. So if you determine the slope of your graph, or you have Microsoft Excel do it for you, you'll then be able to manipulate this last equation here to calculate a value for the acceleration due to gravity. Your value should be pretty close to the accepted value of 9.8 meters per second squared. And that's, again, what we're trying to check in the lab. So you're going to kind of pull all these pieces together. The equation that you're trying to verify is this, and your two tests for verifying it is if you get a linear graph when you plot period against the square root of length, and if you get a value for the acceleration due to gravity, which is close to 9.8 meters per second squared. Now, the lab exercise that's attached to this is going to give you some more steps to walk you through this, but this will give you kind of the overview of what we're looking at. Just to conclude, I'm going to mention the references here. This is in reference to the Camosun College Physics 104 lab manual, from which the lab is based and which inspired this video. Thanks for watching.